Special Theory of Relativity. Lecture 2. Motion under the action of a force in relativistic mechanics. Part 1. The relativistic equation of motion under the action of a force. Previously, we considered the relativistic effects that occur in freely moving bodies. The velocity of such bodies remained constant. Let us now consider how the motion of a relativistic body changes under the action of an external force. Now, the body's velocity will decrease or increase, depending on the direction of the force. The equation of relativistic motion under the action of a force will be identical in form to Newton's equation. The time derivative of the body's momentum will still be equal to the force. However, since momentum is the product of mass and velocity, and the mass of a moving body depends on velocity, when differentiating momentum with respect to time, in general, it is necessary to differentiate not only the velocity but also the mass. Physically, this is due to the fact that not only the velocity but also the mass of a relativistic body under the action of a force changes over time. Part 2. Force directed along the direction of a body's motion. If the force is directed along the direction of the body's motion, then differentiating the momentum with respect to time leads us to the conclusion that the same force accelerates a relativistic body less than a non-relativistic one. The magnitude of the acceleration caused by the force in the relativistic case decreases by the factor equal to 1 minus the square of the ratio of the body's velocity to the speed of light raised to the power of 3/2. Thus, the faster a body moves, the more difficult it is to accelerate or decelerate it. Note that the reason for the decrease in the acceleration caused by the force is the change in the body's mass with a change in velocity. One could say that part of the force acting on the body is expended not on accelerating the body, but on changing its mass. Thus, in relativistic mechanics, the force changes not only the acceleration of the body but also its mass. Thus, the accelerating effect of the force weakens. This situation appears as if the force itself, acting along the direction of motion, has decreased. Part 3. Force directed perpendicular to the direction of motion of a body. In this case, the velocity changes only in direction, remaining constant in magnitude. Therefore, the mass of the body will not change with time. Therefore, in the original equation of motion, only the velocity needs to be differentiated with respect to time. The result is an equation of the usual form: the product of mass and acceleration is equal to force. Since the mass of a relativistic body is greater than that of a non-relativistic one, the same force will accelerate a relativistic body less strongly than a non-relativistic one. However, the weakening of the accelerating effect of the perpendicular force will be less pronounced than that of the parallel force. The magnitude of the acceleration caused by the force in the relativistic case decreases by the factor equal to the square root of unity minus the square of the ratio of the body's velocity to the speed of light. Thus, both parallel and perpendicular forces accelerate a relativistic body weaker. Part 4. Force directed at an angle to the direction of the body's motion. In this case, the force will have two components, one parallel to the body's velocity and one perpendicular to the body's velocity. The parallel component of the force will accelerate the body less than the perpendicular component. This means that the direction of acceleration will not coincide with the direction of the force. However, the attenuation of the accelerating effect of a perpendicular force will be less pronounced than that of a parallel force. Specifically, the acceleration component along the direction of motion will be relatively smaller. Therefore, the angle of deviation of the body away from the initial direction of motion will be greater than in the non-relativistic case. It can be said that a relativistic body is more inclined to change the direction of its motion than a non-relativistic one. The coincidence of the directions of force and acceleration occurs only in special cases when the force is parallel or perpendicular to the body's velocity. Part 5. Anisotropy of mass. The misalignment of the directions of force and acceleration can be interpreted as anisotropy of the body's mass. That is, the mass in the transverse and longitudinal directions is different. Note that there is no logical contradiction here, because mass is only a measure of a body's inertia. Therefore, the fact that the values of the body's mass in different directions are different only means that the inertial properties of the body in different directions are different. Part 6. Gravitational force. The above discussed laws governing the action of a force on a relativistic body do not apply to the force of gravity. Since the force of gravity is proportional to the mass of the body, an increase in the mass of the body will not lead to a decrease in the acceleration caused by the force. There will also be no difference between the action of the force of gravity along and perpendicular to the body's motion. The direction of acceleration will always coincide with the direction of the gravitational force. Thus, the force of gravity will act on a relativistic body in exactly the same way as on a non-relativistic one.